Hi guys, in this video I will talk about mainly the current sources because it is very important also to study PNP, to study the PNP and NPN current sources with with and without Opamp, and of course even implement simple voltage regulators. Now you may think that these circuits are basically useless because you can buy voltage regulators, you can buy current source, precise current source already made on the market, and you are not far from the truth. But in reality, these circuits are employed also like in this case in an external LDO. So basically, you buy an LDO. And if you want to extend the current capability of this guy, which is more or less 50 milliamps, in some sensor application, you may need current greater than this. To extend the current capability, you should implement a current source circuitry like this. So basically, this net here is called a pass transistor net, and it enables and disables the input of the LDO. Basically, this MOSFET, this PMOS Q2 must be high enough to sustain the input current that you want to feed. And then this resistor here, this transistor here, plus the resistor R1 enhances the current capability of the volt of your low dropout regulator. Then this, of course, is the feedback net which set out the voltage. This is no connect, so we don't care. And of course, this is the input and the output capacitance as well. So the current flow into here is basically follows a very simple trick. This is the base of the transistor, and this is the emitter of the transistor. To turn on, you should think on the contrary. You do remember that a normal transistor NPN must when it is on, it has a VBA greater than 0.7. Now in the PMOS is contrary, so you study the VAB instead of the VBA. But by the way, you perform a first Kirchhoff law here, and then you will find with some simple calculation that the current flow into here, it is the current load over beta plus 1 plus this contribution here, which is basically given in this branch. So because the output current flow into here, the output current flow into here, I LDO, will be also the sum of this. And this is given mainly by the other contributes. So this is an example on why these circuits are important and why you should consider them. Also in the previous video, in the previous video, when we studied the current, when we studied the transistor implemented analog heater, here I use something similar. It's a different technique, but the concept is the same. You perform a Kirchhoff law here, and you study the VBA over R to have the current protection, current source. Now I will show you different techniques. There are also very famous. You can find at least 20 different circuits of this. So let's start immediately. The first will be a combination of Opamp plus PNP. This is also one of the most common. I repeat, there are more than 20 circuits. So I will only illustrate 3 of them, but and even 4 if I can have time. So let's start with the Opamp plus the PNP combination. You start by giving a voltage here, let's say 16 volts. I don't care about the calculation in this case, and let's use the universal Opamp+2. The universal Opamp+2 is one of the best, and let's call this net V+, and let's apply the Opamp with V+, and let's put everything to ground. Then we connect. Then we gonna do is to use a PNP here, okay, which is commanded by the base, and we perform a feedback by clamping its VBA. In this way, we will have that the positive voltage of the op-amp will be clamped to the negative voltage, which we choose by a divider here. So let's say that I put a voltage. I can even put a voltage directly with, not with a divider, but I don't care. Let's choose, for instance, yes, this has a very big IC current. So we will put a capacitor as a load. This capacitor here we will call the node C, and this capacitor here will have will start with 0 voltage, so that we will have a very big load at the beginning. And if we don't protect this if we don't protect in some way somehow this voltage, we will have basically 10 amps, 100 amps of spike current. So we need to protect this capacitive load some way. And the way to do this is to put a resistor here, let's say 5 ohm, and to connect to the voltage power supply. If you run the simulation for this is a very big capacitor, so let's say 1 hour. You see that this resistor here is clamping the current to 100 milliamps. And I have 50.56 volts, which is the same of this. So if I decrease the divider, let's put half and half, I have 80 volts, and the same 80 volts I will have here. Of course, that will change the current, and that will change how many times it stays clamped. This is one of the most basic circuit, and the principle is that you have V plus equal to V minus. V plus equal to V minus. Okay, so at this point here you have V plus. V plus. V plus. You have the V plus of the op-amp, and the current flowing into this. Now you have 16 volts here. So the current flow into this resistor will be I equal to 16 minus 8 over 5. And the result is 16 minus 8, it is 8. 8 over 5 is, let me use the calculator. 8 over 5 should be 1.6. And in fact, you have the limitation to 1.6 amps. Okay, you have the limitation to 1.6 amps through this event here. And the capacitor will charge linearly. The problem of this circuit is that you don't control the voltage in which the capacitor is gonna charge. So you suppose that this circuit is fine if you want to charge the capacitor through 60 amps. Or, basically, if you want to clamp the load to 1.6 amps. You can decide the current through this equation here. So very simple. The disadvantage of this circuit is that it requires an op-amp, and this op-amp, as you may know, it can oscillate under certain condition. So we want to study some circuit without the op-amp. Okay? It will be better to not use the op-amp to do this circuit here, because the op-amp can oscillate. So let's write this. It can oscillate under some load condition, which is something that you don't want. And I can show you that later, the unwanted oscillation of the op-amp. Especially when you have to drive a MOSFET here. So let's study the same circuit, but without the op-amp. Let's study the combination of double PNP plus Zener. The double PNP configuration. The double PNP configuration, it's again very simple to use. Let's say that we have again 16 volts, and now we have to implement the current protection. The current protection. The way to do that is to, let's use a PNP. It is very similar to the trick that I explained before. You have to perform the Kirchhoff's law around this circuit here. And the way to do that, you can either put a resistor, like I did, but there is also another technique, is to put a diode. You have probably seen this circuit around some schematic, is to put a diode here. Let me put a real diode, because it is important. The thing is, you're saying that this voltage, the base voltage here, will be always lower than 0.7 the emitter. So this is the emitter voltage, and this is the base voltage. Thanks to the diode, you're saying that the base will be always 0.7 volts lower than the base, and it will keep this guy on. When this condition is not respected anymore, this transistor will not be activated anymore. The scope of this transistor is that it can steal current from an active device, and to do that you should put another PNP, and now this pair is gonna work, because for a very simple reason. When the transistor Q2 is active, so when Q2 is on, steal current. It will steal current. It will steal current from this device here. Okay, and that will limit the current which is flowing in Q3. So let me put the same here, and let's use again the same capacitor, and let's use the voltage, let's call this node K, and let's say that .IC of Vk is equal to 0. Now, I want also to put 1 kilo ohm resistor here, because I don't want to leave floating voltages, because it is not very... Let's always close this. And let's run a simulation, and let's check the current flow into here. So again, the same. You have again a limitation. So you see that the current is clamped to 50 milliamps. The clamping of this current depends on on this transistor here. And if you change also the Zener, you will if you change the diode, it will change, of course, the current limitation. Now I changed this to 80 volts of difference, and so you see that when it is active, when when you have the difference between the emitter and the base higher than 0.7, sorry, the current limitation is active. And since the current limitation is active, this transistor is stealing 10 milliamps from this. It is stealing current from the base. Stealing current from the base, as you can see, you have minus 50 milliamps, but to the other side. And this means that the current is actually flowing in this way. Check the verse, it is also important. You see that the symbol is flowing, you see that the measurement is taken from left to right, but here it is saying minus 50 milliamps. So it is saying that there are 50 milliamps plus 50 milliamps flowing to this side here, to the left side, which is basically the collector current. And of course, also part of this, part of this 1 kilo ohm resistor. By stealing current to the base, you're reducing the current that this transistor can drive. Remember that the equation is always IC equal to beta times IB. So by reducing the current of the base, you reduce also the current of the collector, and you have exactly what you want: a clamped current load, 50 milliamps. Now you can change this guy as you prefer, but I think that you got the picture. The equation is always that when the emitter base VA is higher than VB, this guy is on, and the transistor and this threshold here will strongly depends on the Zener. So this is also one way to set the voltage current set by voltage drop. The problem of this circuit here, so now in this circuit, the thing is that we have removed the op-amp, and we have still the current limitation to 50 milliamps, which I can do also in this way by putting 10 ohm here. Let's raise it a bit. Let's raise it a bit until we have 50 milliamps. Now you start to see the difference. This is more stable. Let me use 60. Okay, now you see the difference. This circuit here has a way more stable current, and this starts to drop a bit within seconds. Why is this? Partly because of this guy here, which has a non-constant current. As you can see, it is decreasing as well. And so part of this is responsible, the Zener, most of this is responsible, the Zener diode. Most of this, basically all of this. And so now you start to see just some difference. This circuit has a more precise current. This circuit, it does not. So now what we want to have, but you see that the difference that neither in this circuit I can program the voltage. They are reaching always the voltage of the power supply, which is something that you don't always want, okay? How can I design a circuit in which I can clamp a circuit like this with only PNP, without Opamp, which can clamp the voltage as well? So, can we have the double transistor plus clamping, plus voltage clamping? And the answer is yes. Actually, it is the most famous circuit probably, and it is called voltage regulator current limited. There are a lot of circuits like this with and without op-amps. So let's draw it. So let's draw the guy. I will draw exactly the same circuit as this, but with the NPN version, so that you can also have the NPN version. So let's draw this exactly the same, but with the NPN. To draw the NPN, now you should connect this to the. You should connect this to the. You should connect this directly to the load here, and now to make the clamping of the voltage, you are gonna set this with a Zener here. 6.2. You should also bias this guy. So it must receive a current, and the base current is not enough to bias this guy. The same is here, but in this case you can have it is connected with the PNP, so it is enough. So in this case, in the Zener current, it is flowing exactly the current. In this case, the Zener current is just used as a clamping voltage. So now you should bias this guy just to have 1 milliamp, and it will be enough. Just like this. You can substitute this with a regulator. So if you go to reference and you go to the end, you can find this guy, which is the adjustable reference regulator. It is exactly the same. You can use a zener or a voltage regulator, doesn't matter. These are shunt voltage regulator. So let's pick this, for instance, but again, it's the same, okay? The only difference is that you have to provide, you have to connect it like this, and you just have to provide here a voltage, and it is done. So let's put a resistor of 1 kilo ohm, and you're done. It is the same. So the difference is that this reference is more precise and the zener is not, because it changes with the temperature. That is the only difference. And now guys, you have everything, because the concept is always the same. You have, in order to limit a current, you have to put a device which steals current from the base. The equation is always the same. IB equal to beta times IC. Sorry. IC, it is equal to B times IB. So you have to put a device here which is connected to the base of this guy. How should I connect it? Like this or like this? Well, the answer is simple. The NPN takes current from the collector. So if you draw the model of the NPN, the current flowing is in this sense here. Imagine like there are diodes, and the diodes is pointed towards the ground. So it should be connected like this. And now what we want to do is that we have to check a condition, like a Smith trigger, that when the voltage VBA is higher than 0.7, Q5 open, 0.7, Q5 on, and steals current. So that's what we want to do. To do this, what we can do is to put a sense current, a sense resistor, between the base and the current, and we say when the drop of this is higher than 0.7, then the transistor Q5 is active and it steals current from the active device Q4. So we put 1 kilo ohm here just as a base resistor, and the resistor R5 is the protagonist of the circuit here. So let's put, for instance, 7 ohms, and then I will show you how to design correctly. Let's put again 10, and let's call this node D, okay? And let's say that IC of VD is equal to 0 again. So now let's run again the simulation. Let's put it like this, and let's check the current flow into this. Now, as you can see, we have an interval in which it is flowing 150 milliampere, more or less, and it corresponds in which the base voltage, base emitter volt. Oh, sorry, I didn't put real. Again, let me put very big. Okay. This can be enough. Okay, so now 90 milliamps are flowing, and the base to emitter voltage is 0.5, because the current flowing into here is generating enough of the base drop voltage to turn this transistor on, and so this circuit is working by limiting the current here. The difference is that this time I have clamped successfully the voltage in which my capacitor is gonna charge, which is 2.2. should be, sorry, should be 2.5, by the way. But by the way, so I can put also a Zener if you prefer. Let's put the diode. Let's put the Zener. Naturally, the Zener must be in the Zener condition, so in reverse brake, otherwise it won't work. So the anode voltage should be less than the cathode voltage. If you put on the contrary, it will be conducting to and it will be a short. Okay, this is important. Now I'm clamping the voltage to 6 volts. Again, I'm losing some voltage for. Ah, yes, because there is. Okay. Of course, there is the drop of this guy here. No. Sorry, I said something not correct. The reason why I'm losing the voltage. Okay, it's the VCE of these. Is the VCE of these. Yes, because the transistor here it has a VCE of 0.2, and yes, this is the reason I'm losing some voltage. So if I have here 6.5, here I have yes 6 dot something, and the reason it should be the VCE of this guy, which I don't know, honestly. So if I put this, probably I will have a different drop voltage. And in fact, it is correct. I have a different drop voltage. And okay, so we discovered the problem. Okay, the VC of this guy. But by the way, now I have achieved both the thing that I wanted to do in the previous circuit. First, I'm clamping the voltage of this guy here, and second, I'm also clamping the current. So I have a current controlled, and voltage clamping load, which is the best that you can achieve with just two components, two transistor NPN, and just a Zener. So you can realize, you can simply realize the circuit here and put the load here. This is probably one of the most famous circuit, which you can also find in some Opamps, and it is very useful. Now let's just suppose that instead of providing a constant current like this, you want to not to charge the capacitor like this, but you want to charge the capacitor with a ramp, so like this. This can be useful in some application because it is the best. It is one of the. It is a way to control perfectly the capacitor charge. So you say that the equation of the capacitor, as you may know, is that IC it is equal to C times dV over dt. So by doing this, you are changing the voltage capacitor by each step. For instance, you want to say that each step charges the capacitor of 25 millivolts per second. If you want to design a circuit which does actually this, so this is the voltage of the capacitor, okay, which is charging with a programmed ramp, you should use a voltage to current converter. The easiest way to do this is to use a MOSFET, and again the Opamp. Let's clamp this guy here. And let's put 12 volts. Let's put a pulse, because yes, you need, this time you need the pulse. A pulse which should be high enough to turn on the MOSFET. So 0, 1 nano, 1 nano. Let us use 5 milli and 10 milli. So just a very low hertz. And now let's connect an NMOS here. for instance this, and let us block the VGS of this guy with the Opamp. Let us put a feedback resistor of 100 kilo ohm, and now you design the current, the programming current you design with the resistor here, R-car. For instance, let us put 10 kilo ohm, and let us put a very an high side load, 10 micron. Just for the simulation purposes, let me put just a diode here, because I don't want the current flowing to the other side. Should be useless, but doesn't matter. Let's just say that we start the external supply voltage to 0 volt. V5, I didn't specificate the 1 nano, 5 milli, and 5 milli. Okay, now the circuit is switching, so the other simulation are not so fast anymore, but it doesn't matter. We don't care. So now let's check the current here. Let me check the voltage. Of course you don't see it. Okay, wait. It's not that the circuit is wrong or something, but it's just that it is hard to see with this time. Let me put 100 milli. And okay, now we should be able to see it. I think that this MOSFET is the worst MOSFET on the earth, so let me take the next one, because this is not how the circuit should work. And also let me put to skip the initial point solution. Okay, so the diode was necessary. So I'm giving here little passes, and the scope of this is to recharge the circuit here with a programmed voltage. If I check the difference between the voltage here, let me delete everything. Okay. Okay, should be fine. Let me check the pulse here. Okay. Un nano, 5 okay, so it was okay, there was just a okay. I don't like the spike, but anyway. It is a little bug. There is a little bug in this circuit. I don't understand why. Oh, finally. Sorry for the wait. Finally, I managed to. So now, as you can see, I'm charging the capacitor with a current which I decide on each period. In this case, 50 microamps, and this can allow me to charge the capacitor with a programmed ramp like this. The reason why this circuit works and in the off interval the voltage doesn't go down, it's because there is a very high off resistor which basically increases the RC to infinite, and so you have also this way to recharge a capacitor. You can of course increase and decrease the pulse, the frequency of the pulse. If I increase it and decrease it, I will change the frequency in which I can recharge the capacitor. This is very useful if you want a frequency controlled charged capacitor. As I said before, there are a lot of circuits, so I could go on for 4 hours talking about this circuit here. Okay. There are more than 20 circuits, and honestly, this is just some of the few of them. And I hope that you like this video, and hope to see in the next one. Thank you guys, and see you in the next video.